How can we define one connective using other connectives, and does that mean we could do without them? Let's consider. Hello, I'm Chico. Welcome to the Philosopher Channel Introduction to Propositional Logic course. Today we're talking about being functionally complete. What does it mean for a set of connectives to be functionally complete? Also, you could call them expressively complete or adequate. Those are other names for the same thing. The idea is this: there are a limited number of possible combinations in the truth tables for what a connective could be. I can show you here on the screen like the different combos that you can have for one-place connective and a two-place connective, and that's really all we have so far. But you can have three-place connectives, and we'll see that in a second or in later videos, and you can have zero-place connectives. A set of connectives is functionally complete if, starting with that set, you can go ahead and define all the other different possibilities just using purely that set. And exactly how that's going to happen, we'll talk about today. But how do you define one connective using others? In the text, we have this kind of long-winded explanation. Connective star can be defined in terms of connectives dagger 1 through dagger n, where star and dagger stand for possible connectives in the same way like alpha and beta stand for sentence letters like A and B, or propositions like A or B. You know what I'm saying? Like they can stand for any different kind of connectives. If and only if, for any formula gamma containing occurrences of star, there is a formula delta that contains no occurrences of star, but may contain occurrences of dagger 1 through dagger n, and contains no occurrence of any connective that neither occurs in gamma nor is one of dagger 1 through dagger n, and is equivalent to gamma. That is, in their joint truth table, gamma and delta have the same values on every row. What the heck does that mean? So here's what they're saying. Let's say you have some connective and you want to define it using these other connectives. If you can use these other connectives to come up with a truth table that is identical to the truth table of your first connective, then they're going to be logically equivalent, right? They're going to be the same, basically the same in logic. So that means that any statement that you make using this connective over here, you could use this set of connectives over here in this equivalent formation to make that same statement. So in that way, you can define this guy using these guys. That was weird. I've never taught logic using just hands. Hopefully you're not listening to the audio, because you would be completely lost. I don't know if the audio would even be useful in this class. Now, what does this look like practically? Well, in the text, Smith gives us an example. If alpha then beta is logically equivalent to not alpha or beta. So let me show you that real quick in using the truth tables. Okay, first, if alpha then beta, only false when the antecedent is true and the consequent is false. Then not alpha or beta. The not flips the T's and F's. And the disjunction is only false when both disjuncts are false, which only happens on row 2. The rest of them are true. So both propositions are of the form TFTT. They're logically equivalent. And that means that you could substitute in the one on the right for the one on the left whenever you wanted to. Let me give you an example. Let's say we had something like this. Whoa, off the screen. A and if B, then if A, then C. Okay, so this one, I'm not going to go through all of the truth tables for this. What I want to show you is how you can substitute in where this is right here. You could substitute in this. Where there's a if A then C, you could substitute in a not A or C. That's going to show you why you could define the arrow using just the not and the or. So what we'll do is just fill out the truth tables for the sub formulas, if A then C and not A or C, and see what happens. And then we'll see how you can define the A arrow C just using the not A or C. Okay, if A then C is only false when you have T in the antecedent and a false in the consequent, that is here and here, otherwise true. The not will switch all the T's and F's. And the disjunction is only false when both disjuncts are false, which is here and here. Now consider what happens in the next step when we add in B. Since those two subformulas have identical truth tables, then they're going to interact with that if B then the subformula in the exact same way. So you're going to come up with the exact same truth table. I won't go through the rest of the truth table because hopefully you see it from here. But that's why you can define if A then C using not A or C, because you can just sort of do away with if A then C and just use not A or C. Interestingly, you can also define the if and only if using just arrows into and. So this is how that would go. If and only if, only true when both component propositions are true or both component propositions are false. That is here and here. Then looking at those conditionals, only false when you have a true antecedent and a false consequent. That is here and here. And then finally, that and is only true when both conjuncts are true, and that only happens on the top and bottom. So you can define the double arrow using just arrows and. Now, if you can define the arrows using not and or, that means given this and in here, we can define the double arrow using the not, the and the or. So now we have three connectives that define two other connectives. And interestingly, you can define one of those connectives using the other two. So alpha or beta is logically equivalent to not alpha and not beta. First, the disjunction is only false when both disjuncts are false. That's the bottom row. Then the nots on the alpha and the beta flip the T's and F's. Then the conjunction will only be true when both conjuncts are true. That's only in the last row. Then the not will flip all the T's to F's and F's to T's. And we have successfully defined the or using not and. That means using not and, we can define or, arrow, and double arrow. We can define all the rest of them using just these two. Kind of interesting. Anyway, for next time, go ahead and do 6.6.2. I originally wanted to do this whole thing in one big chunk, and I realized as I started doing it, there was no way that was going to happen. So we're going to break it down into parts and yeah, do 6.6.2, and I'll see you in that video. Adios.